Hey everyone, and welcome back to this series on Foundation of Math. In the past couple of videos, we've been primarily focused on linear relations, or linear functions. We also talked about some linear inequalities, some applications of linear functions, and also looked at how to solve systems of linear equations, in particular with the 2x2 case. Now what I want to do is increase the degree just by one and take a look at some of the fundamentals associated with quadratic relations. So firstly, what exactly is a quadratic relation? And we're going to be primarily focused on the perspective of functions, but generally speaking, we can rotate this quadratic relation around to get, other quadratic relations that are not functions. So a quadratic function will be of the form f of x is equal to ax squared plus bx plus c. So if a is equal to 0, we're just going to be left with this bx plus c term. So we're going to be assuming that a is not equal to 0, so that this is indeed not a linear relation. So this particular object is referred to as a quadratic function. And its graph is usually what we refer to as a parabola. So the graph of a quadratic function, called a parabola, and typically is drawn sort of like a U. So parabolas are U-shaped. So if we take this object, f of x, and we set it equal to 0, then we're going to get a quadratic equation. In particular, ax squared plus bx plus c is equal to 0. And since we have this particular object, you can complete the square on this, and we can get something called the quadratic equation. In particular, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This object, underneath the square root, is sometimes referred to as the discriminant of the quadratic function. It's the discriminant of the quadratic function, or one could also say it's the discriminant of the quadratic equation. Depends on the context. So sometimes people will also represent the discriminant using capital letter delta, which kind of looks like a triangle. So there's a couple important things about discriminants that are important to mention, because the discriminant is located under the square root. And if you don't like imaginary numbers, then you can't take square roots of negative numbers, right? So, then we can't have imaginary objects. So case 1 is the case where the discriminant, delta, is equal to 0. Keep in mind, when we set an object equal to 0, what we're actually finding is the x-intercepts. So the x-intercept for this particular parabola will be equal to negative b plus or minus the square root of 0 all over 2a, which is just negative b all over 2a. So there's actually only one x-intercept. Only one x-intercept. Sometimes people also say one root, right? Because if it doesn't cross the x-axis, then it doesn't have any x-intercepts, right? But this object can be viewed also as a root of that particular quadratic equation, or a root of that particular quadratic function. So if a U-graph only has one x-intercept, then what will it look like? So if it only touches once, then there's only a couple ways that it could look like. It could touch at that point there, or it could touch, for example, at this point here. So if this orientation is x on the horizontal and y on the vertical, that is typically the case, then this purple graph actually is associated to parabolas where a is greater than 0. And when our parabolas are facing downwards, that's evident when the leading coefficient a is negative, right? And if that is the case, then in either of these cases, whether it's positive or negative, this object, which we usually refer to as the vertex of the parabola, which is either a minimum in the case that a is greater than 0, or it's a maximum in the case that a is less than 0, is the location of the x-intercept. So when the discriminant is equal to 0, then the x-intercept is actually located at the x-coordinate of its vertex, which is equal to negative b divided by 2a. So you actually get the equation of the vertex of a parabola simultaneously to this, and using some calculus, there is also a couple more other ways to get it. in addition to symmetry of parabolas, because in case you can't see, the parabola is actually symmetric about that vertex vertical axis. Right? So that's the first case, that the discriminant is equal to 0. Let's look at case number 2. And case number 2 is going to be if delta is positive. So if delta is positive, then the x-intercept will be equal to negative b plus or minus the square root of delta, all divided by 2a. And since delta is a positive number, the square root of delta is also a real number. Therefore, this object will be a real number. In particular, there's 2 real numbers because of that plus or minus sign. So therefore, we have 2 x-intercepts. And we will also say it has 2 real roots. So what would a parabola look like if the discriminant is positive? Again, we have a couple cases, whether a is positive or a is negative. So if a is negative, then those would be the locations of our 2 roots. And if a is positive, i.e. the parabola is facing upwards, i.e. its vertex is a minimum, then we can clearly see that our x-intercepts, i.e. our real roots, are looking at those 2 particular positions. Now let's consider case 3, and you might want to pause this video to sort of see if you can fill in the details here. So case 3 is if our discriminant is negative. So if the discriminant is negative, that means that the square root of delta is an imaginary number, right? And just a quick refresher of, imaginary numbers. If you have the square root of negative 4, this is equal to 2i. The square root of negative 1 would be equal to 1i, which some people just refer to as I. And the square root of minus 5 would just be the square root of 5i. You could also write it as the square root of 5i. Just make sure you don't write the I underneath the square root. So these all are objects that are not real numbers, right? So the square root of delta is imaginary. That means that our x-intercept, which is equal to negative b plus or minus the square root of delta all over 2a, this is not on the real axis, right? So we can't say it has any roots because it doesn't have any in the real plane, so it has no x-intercepts, but we still say it has 2 roots, but we will say it has 2 complex roots. Sometimes people will prefer to write our complex roots in its real and imaginary components, so we can write this instead as negative b all over 2a plus or minus the I times the square root of the absolute value of our discriminant, right? So we get this particular part where this is the real part, and this is obviously the imaginary part of our complex roots, because keep in mind, complex numbers usually have 2 parts, the real and imaginary portion. So what would the graphs of a parabola look like if it has no real x-intercepts, i.e. it has 2 complex roots? So we would have this particular scenario or this particular scenario where it doesn't cross the x-axis. So this is obviously when a is greater than 0, discriminant negative, and this would be a less than 0, discriminant negative. So those are the 3 cases for quadratic relations where the discriminant is positive, negative, or 0, and whether the leading coefficient is positive or negative, which dictates whether the vertex is a local min or local max. And also, from this discriminant analysis, we were able to build the formula for the location of the vertex. So let's actually take a practical working example and find out everything we can about that quadratic function. Let's consider the quadratic relation given by the function f of x is equal to 2x squared minus 5x minus 3. When you don't have the quadratic function factored, or you don't have it written in any strange way, i.e. it's written in ax squared plus bx plus c form, some people will usually refer to this as the general form of the quadratic function. So what can you say immediately about this function? Well, its degree is equal to 2, which means the graph has a parabolic shape. Also, the leading coefficient a is 2, which is positive. So if the leading coefficient is positive, then what can you say? So that means the parabola faces, so does it face upwards or downwards? You should say upwards since it's positive. If A was negative, it would face downwards. And if it faces upwards, that means the vertex is is it max or min? You should say it's a minimum, right? So where is this vertex? That is a minimum. So the vertex, keep in mind, generally speaking, its x-coordinate, is located at negative b all over 2a. Here a is 2, b is negative 5, and c is negative 3. So for our example, that's going to be negative b, negative 5, all over 2a, which is 2 times 2. So negative negative makes a positive, so we're going to have 5 divided by 4, i.e. 1.25 as a decimal for our x-coordinate. And the y-coordinate of the vertex will be just equal to f evaluated at the x-coordinate of our vertex. So plugging 5/4 in and doing some fraction math, that's going to give us 2 times 5/4, the quantity squared, minus 5 times 5/4, and then minus 3. And I'm going to put that over 1 because we're going to have to get some common denominators here. So 5 squared is 25. And 25 times 2 is going to be 50, and 4 squared is going to be equal to 16. 5 times 5 is going to be 25 divided by 4, and we're going to have to get a common denominator, so I'm just going to multiply that by 4 now. And then we're going to have 3 over 1, and that's going to be multiplied by 16 to get that common denominator as usual. So once I have that particular object, then we're going to have 50 minus 25 times 4 minus 3 times 16 all over 16. So once you do 50 minus 25 times 4 minus 3 times 16, you should get minus 98 all over 16, which can reduce by a factor of 2 to minus 49 all over 8. Right? So that's the x-coordinate of our vertex and the y-coordinate of our vertex. So that means f has a vertex, and that vertex is a minimum located at the point 5, 4, negative 49 eighths. Some people also say, in terms of letters, that h comma k is equal to 5 fourths negative 49 eighths, where h is the x-coordinate of the vertex and k is the y-coordinate of the vertex. Right? So that's how we can find the vertex for an arbitrary parabola. Let's go ahead and see if we can sketch this function out. So again, let's bring back our function. F of x is equal to 2x squared minus 5x minus 3. If you find f of 0, we can clearly see that f of 0 will be equal to minus 3. So that means the y-intercept will be equal to 0 minus 3. So we can include in that our sketch, inside of our sketch. So once we sketch this out, let's put our 0 minus 3 right there. Our 5/4, which will be located there. And you should be able to note that minus 49 over 8 is actually less than minus 3. So let's put our minus 49 over 8. You can look at the decimal to sort of convince yourself of that. So we're going to have our vertex located there. So let's build our parabola. Let's make it as u as we possibly can. So that's going to be our parabolic function f. Let's label our axes also. Let's label that as x. Let's label that as y. Right? So there's our vertex there, which is going to be our 5/4 and negative 49 eighths. And we also appear to have a couple x-intercepts as well. We know it has 2 x-intercepts because our a is positive. Our discriminant appears to be negative, but how do I know it has 2 x-intercepts that are real if I haven't calculated the discriminant? Well, if the vertex is underneath the x-axis and it's facing upwards, and since this is a smooth parabola, and it's in some sense continuous, it doesn't have any gaps, then it has to cross the x-axis at least 2 spots, right? In particular, it's there and there. Now, in terms of our sketch, how do I know that one x-intercept is negative and one intercept is positive? Well, it has to go from, a height of negative 49 eighths to negative 3, and it cannot go backwards. It cannot sort of, turn directions and go like that way. It can't go that way because it has to pass through 0, minus 3. So it has to pass through somewhere to the left of x is equal to 0, and it has to pass somewhere that is to the right of x is equal to 5/4, right, by the smoothness of this parabolic function. Right? So what exactly are those particular points, these x-intercepts? So our x-intercepts, let's actually calculate our discriminant just to make sure that that is positive. So that's going to be equal to b squared minus 4ac. So that's going to be equal to 25 plus, because it's minus times a minus, 4 times 2 is 8, and 8 times 3 is 24. So we have that our discriminant, delta, will be equal to 49. So it's actually a very nice number. It's positive, nonetheless. And also the square root of delta will be equal to the square root of 49, which is actually a pretty nice number. In this case, it's equal to 7. Right? So that means what? So that means that the x-intercepts will be equal to negative b plus or minus the square root of delta, which is 7 all over 2 times a, which will be equal to 5 plus or minus 7 all over 4. So our x-intercepts are both rational numbers. So that means our first x-intercept, which I'm going to call xi1, will be equal to 5 plus 7 all over 4, which will be equal to 12 over 4, which will be equal to 3. And our second x-intercept, which I'll call xi2, will be 5 minus 7 over 4, which will be equal to minus 2 all over 4, which will be equal to minus 1/2. Right? So we can include those into our graph. So that's going to be x is equal to minus 1/2, and that point obviously would be equal to 3. Minus 1/2 obviously is less than 0, and 3 obviously will be greater than 1.25, i.e. 5/4. So our sketch so far is up to par. Also, one interesting thing to keep note, if you always have rational zeros, or rational x-intercepts, that means you actually could have factored the original quadratic relation. You should be able to complete the square using AC methods or what have you. You should be able to show that this factors into 2x plus 1 and x minus 3. And you should be able to see that just from these x-intercepts here, right? But sometimes, we don't want to sort of try and factor it. Quadratic equations usually can reverse factor that as well, right? And again, sometimes people will call this expression the factored form of our quadratic relation. Now up to this point, we have two representations of a quadratic function. We have the general form and we also have the factored form. But there is one other form that does have a lot of applications, and that's actually in terms of its vertex. But before I actually just define it and then do an example of it, I will actually want to look at our quadratic relation from a different angle. In particular, let's just look at our quadratic function f of x, which is just equal to 2x squared minus 5x, and then we have our minus 3 term here. So what I want to do is I actually want to complete the square on just these first two terms, and notice that our leading coefficient is not 1, so we have to factor that out and deal with fractions, but that shouldn't be a worry at this stage. So we're going to have 2 times, and then we're going to have x squared minus 5/2 x, and then I'm going to leave this constant term at the end alone and leave that till the end. So we're going to take this number in front of x, we're going to divide that by 2, i.e. negative 5/4, and then square that. That's going to give us 25/16. So when I do that, that's going to give us 2 times x squared minus 5/2 x. I'm going to add 25/16 and then subtract it, so I keep my equation balanced. And then, if you remember anything about completing the square, those 3 terms will always factor. In particular, what two numbers multiply together to give you 25/16 and adds together to give you negative 5/2, you should say, oh, that's going to be minus 5/4 and minus 5/4. It's actually always that number divided by 2. So once you do that, that's going to be pretty nice. So that's going to give us x minus 5/4, the quantity squared, and don't forget that 25/16 that's still chilling on the inside of that bracket. Now let's distribute this 2 into that first term and that second term and simplify that. So that's going to be 25/16 times 2, which is just going to be 25/8. So now we're going to have 2 times x minus 5/4, the quantity squared, and then minus 25 over 8. And then we're going to have this minus 3 over 1, for which we're just going to multiply by 8, so we can combine those last two terms together. Once we do that, we're going to have another representation of our function. In particular, f of x is equal to 2 times x over x minus 5/4, the quantity squared, and minus 25 minus 24 will be equal to minus 49 over 8. And then we have this form, for which some people refer to as the standard form of the parabola. Now, is there anything special about this that you see? Well, you should notice that 5/4, that's just the x-coordinate of our vertex, and this object here is going to be the y-coordinate of our vertex. So what you actually see here is the standard form of a parabola is actually equal to a times x minus h squared plus k. And if you remember transformations about parabolas, for example, let's assume that we have an a that's equal to 5 and a vertex equal to, say, minus 3, 2 for a parabola. So what does that minus 3, 2? Well, that means that we're just shifted to the right 3 units and up 2 units. So that means this would be our parabola, and it's 5, technically it's not drawn to scale, but it would be phasing upwards since that would be positive. So the standard form of our vertex, or for this parabola, would be f of x is equal to 5 times x minus negative 3, so x plus 3, the quantity squared, and then plus 2. So that would be the standard form. Right? So we have the standard form, very useful for vertices. We have our factored form, very useful for x-intercepts, and we have our general form, which is very useful for y-intercepts, right? So each of these forms do offer something useful to the story. Not one is superior, at least absolutely, than the others. So remember when we first started talking about linear relation fundamentals, we were starting with this idea that if you have 2 points P1 and P2 in a plane, and now we're going to be assuming that the x values are different, so you can have like a vertical line, which wouldn't be a linear function, but it's still a linear relation, then there always exists a unique line that passes through them. That is, we can find the slope, we can find the intercept of that line and be able to find those numbers, m and b, y equals mx plus b, for that linear relation representation. So do we have actually a similar result for parabolas, i.e. quadratic relations? For example, if I give you 2 points or 3 points or 5 points, does there exist a unique parabola, that passes through them? The answer actually for this is yes. So let's actually take a look at what that statement would look like. So let's assume that we have 3 points, P1, P2, and P3. And let's assume that they are all non-linear points. That is, the slope between P1 and P2 is not equal to the slope of P2 and P3, and the intercepts of those lines are not the same, right? So they're not collinear. So non-linear points, aka non-collinear. Non-collinear, another way of saying it. And let's assume that they belong to a plane. And let's also assume that they have different x values. Then there exists a unique parabola that passes through them, right? So now we're looking at 3 points and a unique parabola that passes through them. So let's sort of see how we can put that to work with a working example. So let's assume that we have 3 points. Let's use -1, 2. Let's use 1, 3. And let's also use 2, 5. And our goal is to find a parabola that passes through these 3 points. So let's use f of x is equal to ax squared plus bx plus c. So what are the numbers a, b, and c such that I plug in -1, I get 2. I plug in 1, I get 3. And I plug in 2, I get 5. So if I plug in -1, what will I get? So this is for point number 1. So we're going to have a times -1 squared plus b times -1 plus c, and that should be equal to 2. If I plug in point 2, I'm going to have a times 1 squared times b times 1 plus c, and that should be equal to 3. And then from point number 3, that's going to be a times 2 squared plus b times 2 plus c, and that should be equal to 5. And then I can clean that up, and I can write that as a minus b plus c equals 2, a plus b plus c equals 3, and 4a plus 2b plus c equals 5. Right? So what do I have here? Well, this is obviously a system of 3 linear equations with 3 unknowns, which is slightly more complicated than 2 linear equations and 2 unknowns, but there definitely exist several different methods to solve linear equations, especially if you know matrices or maybe even some clever tricks from a field called linear algebra. So let's assume that you have all of those objects and you can solve this particular system with whatever methods you have in your fingertips. And you should be able to find that a is equal to positive 1/2, b will be equal to positive 1/2, and c will be equal to 2. If you're not convinced of this result, try and plug these 3 numbers into that system, and you will get 2, 3, and 5 for each of those equations. And if you look at these numbers as the coefficients of our quadratic, in particular f of x is equal to 1/2 x squared plus 1/2 x plus 2, and plug in your points that we had before, -1, you should get 2, 1 you should get 3, and 2 you will get 5. And using some other fancy theories from other courses, one can show that this formula f of x is actually unique for these 3 points. So those are some of the basics associated to quadratic relation fundamentals. In the next video, we'll look at some real-life applications associated to quadratic relations. Hope you enjoyed this video, and I'll see you in the next one. Take care.